Okay, we are on chapter 14 here, and we got into really buffers last time. So if I can find my pen here, there it is. So remember that buffers are a solution that can resist changes in the pH, even if you add additional acid or base to it. And what we're talking about is, again, as we talked about last time, it is a solution that it has the ability to resist really big changes in pH. The pH will move a little bit, but if it's a good buffer, you shouldn't see a pretty giant kind of shift in the pH if it's sort of functioning correctly. The way it's able to do that, as we talked about, is really what makes up a buffer. And remember, a buffer has to be either a combination of a weak acid and the salt of its conjugate base. And remember, that really is just the basic Bronsted-Lowry definition between acid and base, 1H plus difference. The salt part of the conjugate base in this case really doesn't do anything. So it's just like, sodium or something like that that's hanging out to balance the charge. Or you can make a buffer out of a weak base and the salt of its conjugate acid. And remember that you cannot have a buffer that is really composed of a strong acid or strong base. And the reason for that, as we talked about, is with a weak acid or even a weak base, what will happen is it is able to sort of in the beaker, if you will, set up this equilibrium. And by doing so, what it's able to do is essentially the important part of a buffer, which is that kind of acid part here and the base part over here. And again, they both really need to be in that solution to allow really a buffer to function correctly. And you can't have that with a strong acid or strong base because it will not set up the equilibrium. So you'll either have, all of like your conjugate base, all of your conjugate acid, but you won't have both components that's necessary for a buffer basically to be able to resist that change in pH. You can, as we'll kind of touch upon as we go through the rest of this chapter, you can actually make a buffer from a reaction of like a strong base and a weak acid, but the buffer itself is does not have like the strong base still there. It's kind of all used up. The result of that reaction actually will make a buffer. And we'll see that actually when we go kind of through titrations and talk about that. The way it's able to really function, because it has both of those components in there to start with, is it's able to prevent really the formation of free H plus when you add acid or free OH minus when you add base to the actual solution. And those are really the two things that, when they are in the solution by themselves, have a pretty drastic effect on the pH. So by ultimately kind of maintaining and not allowing free H plus into the solution in a buffer or free OH minus into the solution in a buffer, what it's able to essentially do, as we talked about, is keep the H plus concentration relatively the same as to where it started from. It will change just a little bit, which is why you see a little bit of a pH change in one direction or another, but it will not change dramatically. And that's why we don't see the dramatic sort of jump in pH if you did make your buffer correctly and it is appropriate for that situation. We also talked about that, and we saw that you essentially will use up part of your buffer when you add acid or base, but you will make the other part of the buffer. So it's almost self-regenerating half of it as you kind of use the other. There is also, as we talked about, buffer capacity, which means you can blow through your buffer if you add too strong of an acid or base, or your buffer is not the correct molarity. It may not be able to handle that. When we look at buffers, the equation that we saw for common ion is really the equation that we use for buffers, and that's what most people refer to this equation being used for, which is buffers, which is the Henderson-Hasselbalch equation. So as we talked about, you can definitely use the Henderson-Hasselbalch whenever you can recognize it is a buffer, because again, a buffer really is a common ion situation. And you could do that and not have to do the ice table. As we also saw and talked about, you can still do the ice table if you want to and not use the Henderson-Hasselbalch equation. So it is really your sort of call on that. The pKa, obviously, minus the log of the Ka value. Using the Henderson-Hasselbalch equation, that also tells us that typically we want to choose a weak acid or a weak base that is plus or minus 1 of the pH of our buffer that we're looking for. And that's, again, how you can kind of choose, what you should make your buffer out of by looking at the pKa values. The last thing we talked about was when we add something to a buffer, or just in general, when we add like a solution to a solution and volumes do change, the molarity also changes. So when we do any type of situation like that, like we did, I think, on the last couple problems, when we add something to a buffer, like additional acid or additional base, you still need to do an ice table. And again, the ice table there is really to figure out what happens to your buffer as a result of you adding either the acid or base to it. But you do need to do it in moles. So definitely got to do it in moles. And kind of one of the different things about the ice table when we typically do it in moles, not all the time, but in most cases, when we do the ice table in moles, we actually will kind of know what the change is. So we typically don't use X a lot when we are doing like an ice table with moles. We actually know what the number is, and that's what we use for the change. In the case of the buffer, if the buffer is a good buffer, the change really should be whatever acid or base you're adding to the buffer is usually the change. The way you should always remember it is with buffers and also with titrations and beyond is you should always choose the smaller number so you don't get a negative number, right? So, it's always keep that in mind. After you're done with that first ice table, as we talked about, is also really good practice just to convert everybody back to molarity using the total volume. In the case of a buffer situation, that would be the volume of the buffer, and the volume of whatever you added to it would give you your total volume. You then can convert it back into molarity. And that's really good practice. As I mentioned, um, typically speaking, though, if you are going to go into the Henderson-Hasselbalch, you can leave it in moles and it will all come out the same as molarity. But if you're getting an ice table, you should definitely be in molarity. And there will definitely be other calculations along the way where you will do a table in moles that you actually do need molarity to kind of continue on. So it's just a safe practice to kind of convert it back to molarity after that table. Any questions on any of that there? Okay, so we did this one, but why don't we mix it up and we'll do the same buffer as we did on the last one, just to do one more here. But instead of HCl, why don't we add some, instead of sodium hydroxide, why don't we add some HCl? Why don't we go with, what would be the pH after we add, we'll go with, why not, 7 milliliters of 0.5 molar HCl. So you don't have to do the first part. We'll just do the part after we added it. Again, I think I gave you both actually, but I'll give you the Ka here of NH4 plus should be 5.6 times 10 to the minus 10. All right, so give that one a go. Okay, let's take a look and see. So once again here, we have a buffer and we are adding, in this case, HCl to it. So clearly we need to do an ice table to figure out what the effect on adding that HCl is to our buffer. As we talked about last time, again, we could recognize this hopefully as a buffer, as these are the two components of it, that NH4 plus and that NH3. Because we need to do this ice table and we need to do it in moles. So once again, we're going to get the moles of everybody. So once again, we do have our 80 milliliters of our buffer here. That does contain, again, both parts really of our buffer in there. So we'll get the moles of each of those guys. Once again, it should be the same as what we had last time. I feel like maybe I'm good there. Liters. So we'll times 0.08 liters, which is our 80 milliliters, times 0.3 moles per liter, which is our molarity of our NH3. And that gets us 0.08 times 0.3, going to get us our 0.024 moles of NH3. We'll do the same thing once again here for our other component. It is the same volume for both of them as they are in the same, obviously, beaker. 0.36 moles per liter for our NH4Cl. And that's going to get us here 0.0288 moles of NH4Cl. And obviously, in this case, we're going to get our HCl moles. Again, dividing the volume by 1,000 gets us 0.007 liters times the molarity of 0.5 moles per liter. And that's going to get us here, too many zeros. There we go. 0.5. Looks like 0.00350 moles of our HCl. Any questions on the calculations so far? Now we need an equation. So when we do add the HCl, which is a strong acid, it is going to react with really one part of our buffer. And since this guy is an acid, when it goes for a swim, it is going to react with the base part, right, of our buffer. So those two guys are going to react. So we'll have our NH3 here. And in this case, we will get our acid donating this over, an H plus basically. And that's going to get us NH4 plus and Cl minus in this case. You can, if you want, keep them together as NH4Cl. It's up to you, whichever way you want to do it, or you can keep them separate. It doesn't really matter. It is basically you get this part of the buffer, right? So we're going to generate the other part of the buffer. Here we're going to go our initial moles. So for our HCl, 0.0035 moles. For our NH3, 0.024 moles. And as we talked about a lot last time, super common error is zeroing out the right-hand side. But again, it is a buffer, which means you do have some of that NH4 plus there. Since I separated out the chloride, I am not going to worry about the chloride. So I'll just kind of put that there, as obviously it's a neutral salt, so I don't have to really worry about it. Obviously, if you kept it together, you just have one thing on that side. Remember here, we know what the change should be in this case, which should be in this case the HCl that we're adding. It is the smaller number, so 0.0035 should be our change all the way across. And that means when we do reach equilibrium, we'll have zero of that, which is good since we put a buffer there. We'll subtract this. That's going to get us 0.0205 moles. And we are adding on the other side. So 0.0035, 0.0323 moles in this case. Once again here, just really good practice to do is convert it back into molarity. We know we had 80 milliliters, obviously, of our buffer. Here we added 7 milliliters of our acid in this case. So that's a grand total of 87 milliliters is our total volume. So we'll divide each of these by 0.087 liters. That will convert everybody back into molarity, which, trust me, is really probably the best move in most cases. And that's going to get us 0.3713. And that will get us on the other side here 0.2356 in that case. Again, if you are not sure what you should do at this point and you got to the end of your ice table should hopefully point you in the right direction. If you look at, again, kind of the two things that we have left over, as we would hope in this case, this is still a buffer. So again, that should point you in the right direction. That means we could still go into our Henderson-Hasselbalch, or you could ice table it. I'm going to Henderson-Hasselbalch here. I do need the pKa value that we got last time, which is minus the log of 5.6 times 10 to the minus 10. That is a 9.25 pKa value. So that's going to get me 9.25 plus the log. Once again, as we talked about, this is our base. It has one less hydrogen. So we want to go with 0.2356 up on top. and 0.3713 on the bottom. And we'll see how I did here making up numbers. Hopefully it did all right. Oops. Maybe like a 9.05. Not bad. I think our original buffer started at like 9.17. So again, it went down, which is what we should expect to happen here as we added acid to it. And again, that's a way you could kind of check yourself as well to make sure hopefully you didn't mess up on the calculation. Any questions on buffers or how to calculate pH? So clearly you need to be able to calculate the pH of a buffer, if you add acid or base to it, if you how to make a buffer, all those things there. All right, so the next thing we're going to talk about then is everybody's favorite topic, which is titrations. Yeah. And I think we got some titrations scheduled for next week, so funness. Yes. So a titration is a technique that's used, and obviously we use a burette usually, right? So we usually use a burette, and we have a beaker or a flask that we add it to. And usually when you do a titration, you usually have two types of solutions. You have what is sometimes referred to as the known solution, and that is really the solution that you know really the molarity of, and you know really the volume that you use. So the known solution is typically the one that you know pretty much everything about. The unknown solution is typically the solution, obviously, that you need to find something, right? Maybe you need to find the molarity. Maybe you need to find the volume, you know, whatever it may be. That is usually the unknown. So we use a known solution to figure out something about an unknown solution. You could also be something like molar mass as well, right? You could figure something like molar mass if you wanted to, too. And we do that through stoichiometry. So we use stoichiometry, right, to help us find that, like you did in the vinegar experiment. You had to figure out a bunch of things like percent by mass, I think, and also the molar mass of an unknown acid. So these are very common sort of techniques. We typically, in an acid-base titration, will titrate until we reach what's known as the equivalence point. And the equivalence point in an acid-base titration is the point where you have reached exactly the moles of the acid will exactly equal the moles of the base. So that is basically your definition of equivalence point, is that point in that titration where basically if you had, for example, acid on the bottom, and you're adding base, both of those moles of each other will equal each other. That's not to be confused with what's sometimes referred to as the endpoint of a titration. The endpoint of a titration is where you decide to stop your titration. And if you're doing a good titration, then hopefully your endpoint and your equivalence point should be hopefully pretty close to each other. How do we know when to stop our titration? We use something like an indicator. And as we talked about in the previous chapter, or we will talk about in this chapter, indicators work over a pH range. So an indicator will work over a pH range. And the most common one, probably you've used the most, is phenolphthalein, right? And phenolphthalein, as we used the other day and also talked about, is colorless in acidic solution, is colorless actually in neutral solutions, but it does turn pink in basic solution. And phenolphthalein, for example, as I might have read on the board the other day, works really between a range of 8.3 and like 10-ish. And once again, around the 8.3, it really is kind of colorless still. And again, it gets gradually pink as you go through that. So the idea is when you choose an indicator, as we'll talk about, you always want to kind of choose an indicator usually that will change color near your equivalence point, because that's usually when you want to stop your titrations, unlike the titrations we will do where you just go past the equivalence point. But usually you want to stop at the equivalence point. It's kind of the end of the reaction. That's where you want to stop it. You want an indicator that will actually change color within that range to tell you basically you should stop your titration. Now, we will talk about, like I said the other day, the most famous saying always when people titrate, which is I only added one drop, right? And my thing went like super pink. I don't get it, right? And then maybe your teacher made you retitrate. Anybody had a teacher make you retitrate if it was too pink? No? Yeah, well, mean teachers. They didn't really need to do that. I'll explain why, perhaps. But um, so as you titrate, we were looking for this pink. That's not a bad pink, actually. But usually when you use something like phenolphthalein, they'll tell you want the lightest color pink that you could get. You got to like hold like a white piece of paper over it to kind of see the pink. That's kind of what you're going for. And that's really because that would put you over here, in terms of pH, and that's probably where your equivalence point was. And that's why you want to really stop really with barely any pink kind of showing. All right, so let's talk a little bit about some titrations. And first off, we're going to talk about a strong acid and a strong base titration. So for example, if we took hydrochloric acid, which is a strong acid, and we titrated it with sodium hydroxide, which is a strong base, this will give you a double displacement reaction, right? And we will get water and a salt like sodium chloride in this case, yeah. So what we see here on the graph is what's referred to as a titration curve. On the Y is the pH, and in this case, that is the volume of sodium hydroxide. For reference point and sake here, what we got going on is our sodium hydroxide up in the burette, and down like in the beaker or the flask is the HCl. So in this case, we're adding base to our acid and doing this titration curve. That is also why we see a typical what's referred to as an S curve here. The pH is increasing as you continue to add the sodium hydroxide because you're continuing to add base to it. So when we look at a titration curve like this, there's really kind of four parts to the titration curve. The first part, our step one here, is before you start the titration. So what the pH is before you even add anything like sodium hydroxide in this case. The second sort of part of a titration curve is all the way from the first drop to right before the equivalence point. So obviously you've started the titration at that point. The third part of a titration curve is the actual equivalence point. And usually you haven't done this before, but on purpose, but past the equivalence point is kind of the fourth part here of the titration curve. So we're going to talk about how to get the pH here in each of these spots along the way and sort of what is happening, so you have an understanding of how you would calculate those things. So let's start with the very first spot here, which is before we start the titration, right? So before we start this titration, that means that really the only thing we got going on in this example is we have hydrochloric acid basically sitting in a beaker or in a flask if you so choose. And if we want the pH of something like hydrochloric acid, how would we get it? The pH of hydrochloric acid can be found by, this is what type of acid? As a strong acid, which means because it's a strong acid, that will pretty much give you your H plus concentration. So that will pretty much give you that H plus concentration. And you could actually go right into the pH equation to get the opening pH of your titration in this case. So because you're starting with a strong acid in this case, and because as we saw, pretty much most of all the strong acids are monoprotic, pretty much whatever the initial concentration of your acid is would be your H plus concentration in this case. Go right into the pH equation and you'll have your opening pH for your titration. So now that brings us to the second part of this titration curve, which is we are starting the actual titration. So in this case, we are definitely starting the titration, which means we are adding sodium hydroxide to our hydrochloric acid. And in this is definitely a situation like we saw with our buffers that we are adding volume to volume. And that means that we are going to have two things occurring here. We definitely are going to have a reaction between the hydrochloric acid and the sodium hydroxide. We will need to do an ice table to figure out what that actually does to our hydrochloric acid that we started with. And when we do that ice table, because we're adding volume, we need to do that ice table in moles. So just like we did with buffers, we will have to do this one in moles. So for example here, for step number 2, We are starting the titration. We are before the equivalence point. We are going to get a reaction. So again, it will be the same one we just talked about there, our hydrochloric acid plus our sodium hydroxide, again going to form water here and our sodium chloride in this case. Now, we do need to do an ice table in this case, and as I mentioned before, this is going to be, has to be done here in moles. So for reference sake, we are starting with this guy in our beaker, and we are adding this guy, right, to it. So I am just going to make up this number so we have a nice simple number to use. So for future reference, that's where the number came from. I'm just going to make it up. I'm going to say that we started with 4 moles of HCl. And again, just made it up. You obviously would get the moles just like we did with the buffer, volume times molarity, right? And I'll give you how many moles that you started with. Now, because I am before the equivalence point, should the moles of my sodium hydroxide, which I am adding, should it be less than, equal to, or greater than the moles of the acid I started with if I'm before the equivalence point? What do you think? Should be, I know at the equivalence point, the moles of acid equal the moles of base, which means that if I'm before that point, I actually have less moles of the base than I do of the acid, right? So I'm kind of working myself up to equal, right? And then obviously past the equivalence point, I would have more moles of the other. So in this case, we would actually have less moles of the sodium hydroxide. Once again, just making up the number myself here, we're going to go with 2 moles. And we're going to go with 0 here. Once again, here we did an ice table with moles, so I kind of know what the change is going to be. At this point in the titration, my HCl, if you want to think about it, is my excess reagent, and the sodium hydroxide is my limiting reagent in this case. So it is going to be the sodium hydroxide is going to be the change, 2 moles, 2 moles, and plus 2 moles on this side. That means when I do reach equilibrium, I got 2 moles of this one, 0, and 2 moles of this one. Trust me when I tell you at this point in the calculation, just like in buffers, you should divide by the total volume. And that would be obviously how much acid you started with and how much base you added to it to convert it back to molarity. And again, you would definitely want to convert everybody back to molarity here at the end. Now, at this point, what you want to look at is maybe what you got going on. So we got this guy here, sodium chloride, and we have HCl. By the way, is that a buffer? The answer is no, right? Because that's a strong acid, right? So they are related to each other, but again, it's not a buffer. We basically have a salt here, which we already know is neutral, right? So not even going to worry. So really at the end of this, what you are left with is the HCl. And that is a strong acid. And because that's a strong acid, much like at the first step here, at this point, you could go right into the pH equation and calculate the pH in this type of titration. So once you start this type of titration, anywhere from the very first drop to before you reach the equivalence point, you basically need to do one ice table. That ice table does need to be in moles. And the purpose really of this ice table is to figure out how the concentration of your strong acid has changed as a result of the reaction with the base that you're adding in this case. And then you could go right into the pH. Any questions on that there? All right, so we're titrating, and then we're reaching to the equivalence point, and we see something interesting as we hit the equivalence point. As I go to the equivalence point, I start to go pretty darn vertical, even past the equivalence point, by the way. Pretty vertical all through there, right? So we see typically a big jump in pH to the equivalence point. And then as we can see there in the graph, we typically will see a big jump past the equivalence point in terms of the pH. That means a couple of things if we think about it logically. Is the volume here, by the way, between the spots, is the volume changing a lot in this case? The volume in this case is not changing a lot. If you go straight down, it's all pretty much in that ballpark right about there. But what happens to the pH within this range? Does it change a lot? The pH in this range changes a lot. So as you approach the equivalence point, it does not take a lot of volume to change your pH a lot. And that is the answer to the question that people ask and say, which is, I only added one drop and my thing went from no color, right, to super dark pink. And that is because if you think about phenolphthalein, you have a pH of 8.3 and a 10, and this is colorless. And this is obviously pink to super fuchsia as you head to the end there. And when you get near the equivalence point, when you add just one drop, it doesn't take a lot of volume to make a big pH change, right? So that one drop could put you pretty much here, and your indicator is now going to jump super dark pink because you added one drop, right? And you now have moved the pH a lot because you're approaching the equivalence point. But if you missed it by a drop or two, you may be here, right? And if you're here versus the actual equivalence point, is there a big difference in the actual volume of that? The answer is no. And that's why if you had a teacher that made you retitrate, that was not nice of them. You probably didn't need to do so. If you were really careful and you only missed it by a drop or two, the volume you would have ended up with would have been the same volume you would have if you hit the equivalence point on the nose. The reason why some teachers make you retitrate, not really because they're mean, is because maybe you titrated like I did when I went to school, which was I was the first one done. I opened that thing up, dropped it in there, and it turned pink. And I said, thank you very much. We should do this lab every day. And I went home, right? So if you weren't really careful, you could open it up and stop and be over here, this color pink and like this color pink and even this color pink. It's all the same pink, right? So in this case, if I did it like that, wasn't very careful, am I close to the equivalence point? I am not. I'm pretty far away, right? And you would be obviously in some trouble in that case. So if you're really careful in the titration and you miss it by a drop or two, it's not a big tragedy. In most calculations that you need to do, you really don't have to retitrate. More importantly is usually your volumes, if you do multiple trials, are about the same. You use about the same volume of sodium hydroxide or whatever you're using to titrate with is really more important. But that again is why sometimes people have you retitrate because they don't know how careful you were. Also why, again, when you do like a half a drop or something like that, when you dilute your drop in there, you get that lighter color pink. Again, you're adding a lot more water, not as strong of a drop, and you don't see as big of a change in that case. Any questions on that there? All right, so now that we know why that happens, let's talk about what happens when we do hit that third point of the titration curve, which is the equivalence point. So at the equivalence point, we are definitely have a reaction occurring. And again, in this case, we have HCl and our sodium hydroxide making some water and some sodium chloride in this case. Once again here, we would need to do an ice table in moles, and I'm again making up the numbers so we have some nice little easy numbers to look at. We are starting with the acid, we are adding our base. So again, if I start with 4 moles of my acid, because I am now at the equivalence point, how many moles of sodium hydroxide should I have? Should be 4, right? Because I'm at the equivalence point. That's the definition of equivalence point, once again, is the moles of the acid equals the moles of the base. Yeah, so that is, again, the definition. Now, I will say that sometimes, or a lot of times, you will come across a problem that will ask you to calculate the pH at the equivalence point in titration and not tell you how much volume to get there, right? So you do have to be able to figure that out. There are multiple ways you could kind of figure that out. First off, you could do M1 V1 equals M2 V2, and you could do that to figure out the volume, for example, of sodium hydroxide, you would need to reach the equivalence point. As long as it's a one-to-one relationship between the acid and the base, you could use that. You could also, if you know, for example, you would probably know the molarity of the sodium hydroxide if you were doing this titration. And what you would know also is obviously molarity is moles per liter. So you would know the molarity of the sodium hydroxide just by what we just talked about. Because it's the equivalence point, you should know how many moles you should have. And you could just rearrange the molarity equation and solve for the volume of sodium hydroxide. And that will also give you that answer. So there are a few different ways you kind of figure it out. Obviously, you could do a stoichiometry problem, which is basically M1V1 equals M2V2. Why do you need to know the volume to reach the equivalence point? Because you may need to convert things back to molarity, right? So you need to know how much volume of the sodium hydroxide, for example, you added to your acid so you could get the proper volume to convert things back into molarity. So again, sometimes they may not actually tell you, hey, you added this much. To just say at the equivalence point, what is it? The pH. This ice table is pretty good. We'll go 0 there. The good news in this is hopefully you can't mess up. There's only one number to choose from, right? So I would choose that number. It is 4 in this case. Plus 4. That means 0, 0. We got 4 moles here. We could use our total volume and convert it back to molarity. So at the equivalence point in this type of titration, we have used up all the HCl. We've used up all the sodium hydroxide in this example, which is basically the definition. And again, the only thing left is this sodium chloride. And this sodium chloride is a salt. And as we talked about, it is a neutral salt. And that means that the pH in this type of titration should end up at a pH of 7. So the only thing you should really have left over at the equivalence point in this titration is water and a neutral salt. So technically speaking, your pH should actually be 7 in this case. Really no need for a calculation. You should actually end up at 7 all the time whenever you take a strong acid, strong base. Also why it's called a neutralization reaction, right? Because you basically make water and a salt that's neutral at the end of it. And that is also what we see here. If we look at the equivalence point, that is a 7 right there as to what we get in terms of the pH. Any questions on that? So let's say you're doing this titration and your thing turns pink, but that doesn't stop you because, hey, you still have sodium hydroxide in your burette. Why not? And you decide, we'll just keep titrating. And you get basically the top part of the curve here. We are going to, as I mentioned earlier, see a jump from the equivalence point past it, and it will eventually level off in terms of its pH. And let's talk about what's happening here at kind of step number 4 here on our part, which is after the equivalence point. So after the equivalence point, we are still adding sodium hydroxide, and we're still going to get a reaction between hydrochloric acid and sodium hydroxide. Still going to give us our same guys here. And once again, we are still starting with this guy and adding this guy here. So we do need to do an ice table here. And again, much like always in titrations, first ice table should be moles. So we're going to start with my 4 moles like we've been doing. But now that I am past the equivalence point, should my moles of sodium hydroxide be less than, equal to, or greater than my HCl in this case? It should be greater than, right? Because again, at the equivalence point, they're equal. We're still adding the sodium hydroxide at this point. So now we're going past equal with the sodium hydroxide and above it. So again, I'm just making up this number. I'm going to go with 6 here, which seems above 4. And we'll go 0. Now, an interesting thing happens at this point in the titration. The change part here. What happens at this point in the titration is my HCl is now my limiting reagent, and my sodium hydroxide is actually my excess reagent. You got to always take, like I mentioned before, the smaller number. And I say that because your mind's going to tell you not to take the smaller number. So make sure you do take the small number in certain calculations. And that will give you, obviously, your positive numbers that you're looking for. Here, that we're going to zero out. We're going to end up with 2 moles here, and we'll end up with 4 moles here. Just like normal at this point, we are going to use our total volume, and we are going to convert it back into molarity. And same thing here, we'll convert this guy back into molarity. So once again, if we look at our ice table here, we have 2 things related to each other. Should I use the Henderson-Hasselbalch equation here? Answer is still no. Yes, that is not a buffer, right? So that's sodium hydroxide and sodium chloride. So that is not a buffer, should not use it. This is super common when people do titration problems, 2 numbers. I want to use Henderson-Hasselbalch in every step along the way, should not do it. So here, when we look at it, again, if we analyze what we got going on in this particular example, we got this one, which is a salt, which once again, as we identified, coming from a strong acid, strong base, that is a neutral salt. So I'm not going to even be concerned about what's going on with that at this point. That really means that the main thing that's going to affect the pH in this case is our sodium hydroxide. And in this case, sodium hydroxide is still a strong base. And because that is a strong base, you could get the hydroxide concentration from it. Remember, that's the hydroxide concentration, not the H plus concentration. That means you got to do a little POH action, right? And subtract 14 and get yourself to the pH at this point. So after the equivalence point in this type of titration, it does require 1 ice table done in moles. The purpose of that ice table is basically to figure out how much strong base you've been dumping in there, basically, or is left over at that point, and you're dumping in there. Once you have that, you could calculate the POH and subtract 14, right, and get yourself to the pH in that case. Any questions on that there? So these are the 4 distinct sort of parts to this type of titration and titration curve. And again, you do need to be able to calculate the pH anywhere along there. So why don't we try one? Let's deal with, let's say you did this titration. What is the pH of a titration of 25 milliliters of 0.1 molar HCl after you add, we'll go 23 milliliters of 0.1 molar sodium hydroxide. All right, so take a moment and see what you end up with. Want the pH of the solution after we add 23.0 milliliters of 0.1 molar sodium hydroxide to basically our 25 milliliters of 0.1 molar HCl. So again, this is the same orientation. We got our sodium hydroxide up in the burette, HCl down below. Yeah. Okay, so let's take a look here. Once again, we're doing titration, kind of the same setup. We got our sodium hydroxide being added to our HCl. So clearly we're going to have a reaction. We're going to need to do an ice table to figure out the pH. And because we're doing a titration, it's a safe bet that first ice table should be done in moles. So that's where I'm going to start. I'm going to convert everybody into moles. So I got everybody in what I need. So for my HCl, again, we got to convert our volume into liters, divide by 1,000, move that decimal 3 places to the left. We're going to times it by the molarity there of our HCl, 0.1 moles per liter. And that will get us there, our 0.025 times 0.1, 0.0025 moles of HCl. We'll do the exact same thing for our sodium hydroxide here. Again, converting our volume into liters. So 0.023 liters times the molarity here, 0.1 moles per liter. Also going to get us there 0.0023. And that's our sodium hydroxide. All right, so we are ready to sort of do our ice table for the most part. Here, we're going to go our reactions. So our HCl plus our sodium hydroxide here. Going to make our water and our sodium chloride in this case. Initially for our moles, 0.0025. For our sodium hydroxide, 0.0023. And at 0, again, we are starting with this guy, and we are adding this gun here. So the first thing that is really a good idea in titration type problems is to sort of figure out where you are in the titration. And that oftentimes can help you, especially when we talk about some different types of titrations coming up. It oftentimes can help you in the pointing you in the right direction in terms of what type of calculation you should be doing. So sometimes it's easier, right, to know what you should be doing rather than, trying to do it as you go along. So kind of like directions, right? If you know where you're going, you got the directions before you start, you should know how to get there rather than maybe just driving around. So I know by just looking at my ice table, which gives me a lot of information, I am starting with this HCl and I am adding the sodium hydroxide. And when I look at the moles of each of those, I can see that the moles of sodium hydroxide is less than the moles of my HCl. And because of that, that tells me I am before the equivalence point in this case. And I know that because at the equivalence point, they should be equal. So what I'm adding is less than, so I'm definitely before the equivalence point in this case. That means that the change I would expect is my sodium hydroxide because at this point, it really is the limiting reagent. And the change would be minus 0.0023, minus 0.0023, and plus 0.0023. Here, that's going to get me at equilibrium 0.0025 minus 0.0023, 0.0002 moles. That's going to give me 0 and 0.0023 moles here. Once again, I'm going to convert it into molarity. So I started with 25 milliliters of my acid. I added 23 milliliters of my base. That's like a 48 milliliters, I think. So I'm going to divide this by 0.048 liters. This guy as well. And that's going to get me here 0.00417. And on the other side there, I'll go 0.00417 here. Like I got the same number. I think I lost me a 0 there. Let's see there. That was the wrong calculation on that side, huh? 23.048. That would be much better there. All right. That's what happens when you use a number that's in your calculator, I suppose. There we go. Do that. All right, so 0.0479 molar on the right there, and I believe on the left here we should be good. Just put it in there one more time. There we go. 0.00417 molar. So again, sometimes people kind of ignore their ice table, and you really shouldn't. Again, if you're not sure what is going on at this point or what should happen, you again could look and see what you have left. You hopefully could still recognize really this is a neutral salt, so I don't have to worry about it. So really at this point, the major contributor here to our pH is our strong acid. And that is what we would expect as we are before the equivalence point. We actually should have strong acid left over after this reaction, and that's going to be our major contributor. That means that this guy right here should be our H plus concentration, and because it's a strong acid, that is all we need to go into our pH, which would be 0.00417 in this case, minus the log here, if I didn't screw it up there, 2.38 at this point in the titration. Any questions on any part of that there? We can see how we did here if we look maybe. Let's see. I think this was this titration. So we're at 23. That is between those two numbers. So that's pretty good. So we must not have screwed this one up too bad there. Any questions on that? So this is a strong acid, strong base titration. We're going to talk about some different titrations, but specifically, these are the 4 sort of ways, depending on where you are in that titration, that you could calculate the pH. And again, you do need to be able to calculate the pH anywhere along that titration curve, I feel like, are like 400 points. Just one question on the exam, just a whole titration curve, 300 points. I'm kidding, by the way. Don't go home and drop. All right. Any questions on that?